So design one end of the one-way slabs, end span of the one-way slab. So they want you to design this end span, that is here, that is end span, meaning that if you have a slab sitting like this, and let's say it's continuous here, then you have these multiple supports. They want you to design this end span. If someone asks you to design here in the middle, don't hesitate, I will show you how you can design the middle one as well. So that is, they want you to design the end span. One-way slab, continuous one-way slab is like what header mentions, is like supported. If I have this basically it has this behavior one way, where it's supported at these two edge, like it's supported like here, and it's supported here. So you have these kind of one way. If I apply the loading on the slab, it will just have a main deflection or the bending happening on this one way direction. So that is the one way slab. Continuous over the four span. So it has a four span, like span number 1, span number 2, span number 3, and if I continuous, there are 4 span. That is to be designed as a suspended floor for a block of townhouse. So it's suspended floor, meaning that it's not on the ground floor, like it's in the ground. You have a slab, and if you have, let's say, this wall, then you have this suspended slab that is just above the ground, that is supported by these walls or something like that. So that is the definition of suspended slab in townhouse. So it's just a townhouse, block of townhouse. The floor is to be supported a imposed live load of 2 kilopascal. So this Q has a 2 kilopascals live load, and then you have something additional, superimposed dead load of 1 kilopascal. So you have 1 kilopascals of dead load given in your examples. Due to deflection sensitive partitions, so you have a deflection sensitive partitions above. The slab is supported by 150 millimeter wide parallel walls. So you have these wall which are 150 millimeters wide. The slab is this one at a clear distance of 500 millimeters, and the standards is represented clear distance by Ln. I will show you where it's written, and it's given here as well. To satisfy the fire and durability, this in the week number somewhere 2, we talk about how you can select the concrete compressive strength. So FC-25 megapascals given to you already. Clear cover reinforcement 20 millimeters. So that is clear cover given to you already. Limit the incremental deflection after attachment. So they have give you the limit that your slab should not deflect more than 1/500. So that's the deflection. So if I want to calculate deflection, I would have, let's say, 500 times L0. Let's say L0. I will show you how to calculate L0. Let's say just a conservative L0 is 5000. Then if I do the quick calculations, 5000 over 500, it shows that approximately 10 millimeters. Your slab should not deflect more than 10 millimeters. You can design your slab which could be deflect approximately 10 millimeter. L0 is not correct, but it could be, let's say, conservative 11 if I put 5100. But I will show you the calculation how you can get the L0. So let's say slab should not deflect more than 11 millimeters. So you need to design. So basically, design of the slab, they need to provide the depth of the slab. They will not give you the depth of the slab. That is the main thing, that you need to calculate how thick the slab is, right? So if you have a slab design, so basically slab design take into account those few things, that how thick the slab, in their standards represented by ds, and you have, let's say, this is support here, supports here, then you put the strip, 1 meter strip, and you need to put the primary reinforcement. If you are thinking of this primary reinforcement goes along the short span. So you can be that is short span and this is long span. So this is primary reinforcement, and you need to have this secondary reinforcement along in this direction. So this is the overall nutshell. So when you design the slab, you generally has to provide depth of the slab or thickness of the slab, depth of the slab, how much RIO in primary, like how much reinforcement you put in the primary direction and how much RIO you put in secondary direction. These are the conditions that, these are the questions typically. These are the questions that you need to solve in the design of the slab. What would be the depth of the slab? What would be the RIO you put in a primary direction? Primary meaning that, let's say you have typical slab, typical one-way slab, this one-way slab, and let's say this is long along this line, and let's say it's supported here like this, and it's supported here like this. This is support, by the way. So the you can take a strip of 1 meters. I will show you that philosophy. So you take a strip of 1 meters, and let's say this is the primary RIO. You put this bar along this line. This is primary RIO, primary reinforcement, and then you have this secondary reinforcement. So these are bottom RIO. So generally, if I draw this cross section red one, if you're looking from this side, if I draw the cross section here, then this blue one would be like this. Blue one, yes, blue one is like this, and then you have this green one. This goes on top of here, or you can draw from this side. If I looking from this side, you will have this blue one, and you have this green one. So how much blue one you provide, how much distance you need to provide, how much distance, that's kind of details they need to know. They need to know what is the depth of the slab. Of course your depth should, of course your slab should not deflect by 11. This slab generally sensitive to the deflections, therefore it should not deflect in 11. So you need to provide the slab depth in such a way that it will have a less than 11 millimeters of the deflections, and you need to provide this RIO to crack control, shrinkage and temperature crack control. These slabs are subjected to this shrinkage and slab one. So that's what the details generally you need to provide. So when you have a slab design, don't too much stretch yourself. It's quite, there are a lot of detail, but it's quite overall is quite simple. It's not that big. Okay, so just follow me. I will open the standards and everything. I think I show you where these are. I think I did not put those details here anyway. So the density of the concrete is given, short-term deflection, short-term factor is given, long-term factor is given, shrinkage, creep and shrinkage strain is given to you. So that data is given to you. Now let's start solving this example. So the step number one, that we always need to find, let me summarize that, we always need to find the depth or thickness of the slab. Depth or thickness of slab. Okay, so that's the basic that's what we need to find. Now, so we need to find this depth or thickness of the slab, and the standards is saying you need to have a represented by ds. All right, that's fine. So now we need to start somewhere. Start somewhere meaning you can have ds equal to 10 millimeter. Look, this is very thin. You're never going to have this 10 millimeter slab, so don't use that. 20 millimeters still too small. Generally speaking, you generally start with 150 millimeter trial, 200 millimeters trial, and 250 millimeters trial. This is typically good starting point of the examples. Look, this is a trial and error methods. Trial meaning we need to try. We don't know which one to start with. Someone might say, okay, I assume 200 millimeter thick slab, and we will check whether it works or not. Whether it works means it satisfies the conditions. Then you go back and reduce to 190 millimeters and check again. You can go ahead and do 180 millimeters because of economy purpose. But I think the books and everyone talk about these kind of help to try with trial depth of the one-way slab. Now these tables you can keep it with you as well. I think in the final exams you will have these tables, and this table is very handy to start your minimum depth of the slab. Okay, if you don't know where to start, basically that's what it says that. Okay, so these tables, it will be with you, okay, in the exams or in the test. You can keep these tables in the test. So there are various range. How do you going to use these tables? There are various range, how 250, 500, 1000. So we are in this range, 500. So let's use this range, span to this one, superimpose qg plus qq. So you have 2 kilopascals, 6 kilopascals. So what would be your 2 plus 1, about 3. So you need to have it in between 2 and 3. So when you have 2 kilopascals, you have 25. When you have 6 kilopascals, you have 23. So look, this is kind of engineering decision. There is no right or wrong answers. Okay, so something you can work it out. So you need to have in between meaning that between 23 and 25. Let's take ln over 22, right? So just in between, because our this superimposed load, what is the superimposed load is that we can see that 2 plus 1, almost 3. So let's take it in between, ln equal to 20. Okay, someone will take it 23 or 25. Is not wrong. It's just try. It's not a right answer. We just making assumptions, but we just want to try somewhere. So let's say trial slab depth using the table above, and from that tables I found that ln over 22 is equal to my trial depth. Look, this is trial depth. Okay, by the way, this is not right. This is just a starting point. And if you don't want to use the table, still fine. You can just start 200 millimeters or 250 millimeters. That still works. Okay, so just this is just the starting point, guy. Every engineers also use these tables in the real world. So this is the around the world. I mean, these tables are standards. If you go America, Europe, these are non-dimensional. That's if you take ln over ds, it is like ln over ds is length over depth ratio is 22. Basically, whatever the length that you have it in the slab is basically this length. Let's say this is ln and this is ds. So basically, it says that okay, maintain your ln over ds ratio 22. That's what it's basically meaning. Anyway, that is 22. Okay, in the exams or somewhere, if you struck, you can just use it 23, 24. That is not an issue based using these tables. Now let's ln is given in our examples. There you go, 25 in the figures. And what is ln? By the way, ln is the clear distance between the slab. So clear distance meaning that if you have a slab here and if you have a support here, then this is ln. Then someone said, "Ooh, that's ln is very hard to remember this ln, and that's name is clear span of the slab. People, can you help me? I don't want to remember." That's okay. If you come across with any symbol that you don't want to remember, you come on the standards and probably go on the front here, and they will define the symbol. So I can help you that one. ALN, so ln, length of the clear span in the direction in which moment are being determining, measure face to face of the support beam, column or wall, cantilever beam, clear projection. So that is the definition of ln, and if you want to have it by the pictures, that is the ln. So let's say ln is given in our figure, which is 5000 millimeter over 22 is equal to ds, right? So that is just the ds. So if I just do the 5000 over 22 using my calculators, I will get ds, trial ds is equal to 227.3 millimeters. Now no one's used 227, by the way. Just if you want to trial that one, no one's used that 227 in real world. We always increment by 10. So always use the round number, because your builder will not going to go and measure 227.23. So let's take 230 millimeter. By the way, I told you this is trial. Okay, this 22 is not like a bulletproof numbers. That is can be changed. So let's take ds depth of the slab equal to 230 millimeters. This is a starting, a good starting point. It's nothing too much tricky. Let's start with 230 millimeters. If it does not work, we can go back and change it. Now we look, as I mentioned, this slab is not going to be sensitive about bending, or it's not sensitive. It will not gonna break in bending. These slabs will not going to break in the bending. They're generally sensitive about the deflections, right? This is the control point. Like in the beam, we have a bending is the control point, is a governing factors in the beam. If you remember that beam was, we done a lot of bending check, moment bending capacity and so on. The bending was 2 weeks we spent on beam bending. So that was the governing factor. It was a strength criteria, that bending. Now these slabs are pretty narrow and wide. Okay, so they sensitive to deflection. So we generally wants to satisfy the depth by doing this deflection check. We call it deemed to conform span to depth ratio reinforcement, and we like to check with this one-way slab and two-way slab. So we're going to use clause 9.4.4.1, and we make sure that whatever the depth of the slab that we try, 230 millimeters, is adequate for these. You know, remember that deflections that is given to us, that this deflection is given to us, saying that okay, this deflection is given to us, let's say 11 millimeters or something, that is given here limit. Let's say this limit is satisfied or not, right? So that's 230. This is the starting point. If it does not work here, there is no point to provide the reinforcement. There is no point to provide the strength check and so on, because your beam is deflecting too much. And if the beam is deflecting too much, there is no way that we're going to use them. So let's start this one. Let's start. This is always starting point, that deemed to conform ratio, LE effective over D, K3, K4, delta over LE, 100 UC, FD. This is troublemaker. Don't forget this 1 over 3. This is easy to forget. And we have all the parameters defined here that I'm going to discuss here. So let's start with clause 9.4.41. This is deemed to conform check. And let's start with clause 9.4.41, and that has a L effective over D less than or equal to K3 K4 delta LEF EC over FD EF over 1 over 3. Right, this equation I just copied here from, for your information, this equation. And by the way, we do this one 2 times. Okay, this is just to check whether trial depth is adequate for performing the calculation, or this is just, again, this is trial. This is not a perfect one. This is again trial check, very crude trial checks. That's what I mean. Now, over the years, when I teach this subject, students get too much confused with these examples, LE effective, L0, and so on. Now look, these examples that you have it here in this taken from the book, they use the symbol called L0. Look at that. Don't get confused between these L0 and LE effective and LN. I will explain you everything. So they use L0. They use delta over L0. And the standards use 1 over 500, and standards using delta over LEF. So because we have given this one in the questions, we can just change this one to L0, both sides. So there will not be any what can I say? It will not be any wrong here to changing both side to by L0. And I will explain you both of them. What is L0 and what is LEF and what is LN? Basically, L effective is a effective span. That is the name of that L effective that is given in the standard. Now, L effective, if you like to know where they have written. So basically, L effective is, if you go back to the start of this 23 page number or something, page number 23, L effective here. Effective span of the member taken as lesser of Ln plus D and L. Okay, so that's clearly given here. So it's basically saying that you have minimum of Ln plus D, comma L. Now, what is Ln? Ln, as I mentioned, Ln is just the clear span. Clear span between the 2. What is D? D is the depth of the slab. What is L? I think we can just find out this L as well. L is a center to center distance between the supports. So L is a center to center distance from here to here. Center to distance is L. So I hope it is clear. If you come across in the test or exam L effective, just work out with L effectives. If you want to calculate L effective, by the way, minimum ln plus D. Let's calculate for our examples L effective. Ln is given to us is 500. So that's fine. Let's put 500. Depth of the slab 5000. Sorry, depth of the slab we assume 230. So let's put 230 there. And L, I think center to center distance, because they have 70. This thickness is 250. So that would be 75 this side, 75 this side. I hope you understand 75, 75 meaning. Let me magnify that. So you have 150 here, you have 150 here, and you have 5000 here. So if you want to calculate the center to center distance L, that L would be 5000 plus 75, because you have 75 here and you have 75 here. So it would be 5150 millimeters, right? So L effective in our case is L is 5150. So minimum of 5230 and 5150. L effective is 5150. So don't get confused that how do I calculate L effective. L effective is basically 5150. Okay, and then you can use it L effective here. If someone give you delta on LEF, you can use it that LEF. But in our case they have given you L0. Now what is L0? L0, I think we can go back again. You don't need to remember that one again. Now L0 is L minus 0.7 times the sum of the value A support at each end of the support. So basically this, I will show you this one in the close too. So basically L0 is given as L minus 0.7 A support on left side minus 0.7 A support on right side. Basically LE0 is like this. That okay, let's say you have this support, and L is a center to center distance, Ln is clear span, and L0 L0 is basically from here to here is L0. How? Because you need to calculate this 0.7 A support. Now they have given you this clause that you can use it. That clause is 6.10.4.2. Let's go there. So 6.10.4.2. 6.10.4.2. Yep, clause 10.4.2. Okay, they have given you here L minus sum of this A support for each end of the span, figure 6.1.4b. So let's go and check 6.1.4b. 6.1.4b. 6.1.4b, that is nice figure here, that you have L0 here, 0.7 A support. What is A support? A support is, by the way, from center to center. So in our case, from center to that edge, in our case it is 75, and you can calculate 0.7 A support. So you have L0. So if you know this center to center distance, then you can just take away 0.75 on left side and 0.75 on right side. You can calculate L0. Now that's calculations that we can just calculate. I think L we calculated. I think center to center distance L was 5150. So 5150, take away 0.7. A support left side is 75, because A support is basically the thickness of the support. So that is like let's say this is 150. Sorry, this is 150. This is 150, and A support is just from 150 divided by 2, which is 75, which is A support. And take away, that is both sides, 75, 75. So let's work it out. This one, 5150 take away 0.7 times 75, take away 0.7 times 75, you get 5045 millimeters, right? So I hope you clear. L effective 5150. There are kind of some difference there. How much millimeter difference? 5045. It's about 105 millimeter difference. Okay, so because our example is based on L0, so we're going to perform the work on L0. But ideally, standards wants you to work with 5150. There is not much big difference if you do it. If someone take it L effective 5150 and perform these examples, it will not be big. It would not be wrong. Okay, so but let's perform with L0 with us. So we're going to work on this one. L0 D we need to calculate. K3. What is K3? K3 is the factors that take into account type of the slabs, whether it's a one-way slab or two-way slabs. So K3 is given here just below the close 9.4.1, and the K3 has given us 1 for one-way slab. So that is written here, just down here. So K3 equal to 1. Two-way slab, next week we're going to work. So don't worry about two-way slab. For one-way slab, K3 equal to 1. K4 is K4 on the other page here on page 147, deflection constant. K4 is called deflection constant, and it has 1.4 simply supported. We don't have simply supported, we have continuous slab. In adjusting span ratio, shorter span does not exceed 1.2, and there is no end where no end span is longer than the interior span. So 1.75 in the end span. So we are designing end span. As you can see in our example, it says that design end span. So for designing the end span, we take K4 equal to 1.75. So let's take K4 equal to 1.75. I'm just working on this one by one. Delta over LEF or delta over L0 given to us. Delta over L0 is 1 over 500. That is just the deflection limits. And someone might say, okay, if someone don't give you that one, I think in the standards it has mentioned some values. If you go back to I think chapter 2 or somewhere, they have give you the nice table for deflection limit for service liability, designed for service liability. In these tables you have delta over LEF 250, 1 over 500, 1 over 500, 1 over 800, 1 over 500. There are different configurations and different deflections considerations. So I think book has taken it one of these from this one. In case if you want to extract informations, the deflection limit, you can get it from here for this equation delta over LEF. Okay, based on the scenario that you want to design. So this delta LEF generally come from these tables. Okay, but in our example it has directly given to us, so we use that. Now delta LEF is done. Then thousands, don't worry. EC, that's okay. Let's calculate EC, Young modulus of the concrete. Young modulus of the concrete depend on the concrete compressive strength, and that is given in, if you remember, there is a table. That table is, let me find, table 3.1.2. we have, I think, 25 megapascal concrete compressive strength given. For that case, EC is 26,700. So for that case, EC is 26,700, and that is coming from table 3.1.2. and where FCDS is given? FCDS is given here. Here you go, 25 megapascal. So EC done. What is next? Next is FD effective. So let's get this FD effective. What is the name of this FD effective? Name of this FD effective is given here, close 9.4.41, and this FD effective has KC as G. There are two equations, by the way, 1 plus KC as G, these short term factors psi s, KC s, IL cube for total deflection, or for the deflection that occur after the addition of attachment of brittle partition or finish. So total deflection, or you want to find a deflection after attaching the partition, so you can use these equations as well. Now in our examples that it says that use the after attached partitions. Let me show you that. The supports this one, slab partition clear distance, this one to satisfy durability, limit the incremental deflection after the attachment. So this is the word after attachment. So I'm just using that after attachment, after the addition or the attachment. So therefore we're going to use this one. If you're not sure, you can use total deflections. If this data is not given to you, you can typically use, but both equations I will show you to you, they are typically same, all the parameters, you're not missing anything here. Okay, but I'm going to use that second one. Now that is called effective design service load. Name is effective design service load, and where it's given is just written here, effective design service load per unit area. Please note these units and all, don't play with those units, just use that as it is. Okay, so the equation is KCSG, which is dead load, plus short term factors plus KCS live load long term factors and the live load. And let's work it out KCS first. Now the KCS is given us, I think in the beam examples, if you remember, for the deflections there was creep and shrinkage factors. Let me find it, that one. Yep, after that. Okay, so close 8.5, 0.3, 0.2, we have given these KCS equations. 2 take away 1.2 ASC over ST greater than 0.8. So let's copy that equations. KCS equal to 2 take away 1.2 ASC over AST and greater than or equal to 0.8. Now for the slab, generally we don't provide the compression reinforcement, unlike slab, let's say 1000 meter strip, 1000 millimeter strip, we generally provide these tensile reinforcement. Okay, we don't provide the compression reinforcement, we don't provide it here on the top. When is let's say if you have a slab like this, and if it is bent like this, and the mid span we have let's say this is bending moment diagram, we provide this in here. If you have at the supports, when you have a negative bending moments, negative bending moments here in this zone, we generally provide the tensile reinforcement. This is tensile reinforcement AST. This is tensile reinforcement AST. We generally don't provide the compression reinforcement for the slab. So ASC is always 0 for the slab. So in that case, if I put the ASC 0 here, that become 2 take away 1.2 times 0, and that would be greater than 0.8. Yes, 2 greater than 0.8. So KCS equal to just give me a minute. So KCS equal to 2. You can see that always KCS equal to 2 for the slab, because your ASC equal to 0. Now KCS is good. Now we need to work out the dead load. Psi S given to us, KCS and live load. Okay, so let's work out this G. G is called dead load, and the dead load would be the weight of the slab, plus dead load that is given to a superimposed dead load. Now weight of the slab, if you remember from your SD2, if you have a slab with the thickness of 230, that was we are trying. So if you want, and density is given to us 25 kilonewton per meter cube, and then you times by this thickness 0.23 meters. So that it will give you kilopascal weight. 25 times 0.23, you get 5.75 kilopascal. That is the weight of the slab, right? And density of the slab given to you that is 25 kilonewton per meter cube density is given to you. Now this 0.23 density of the slab given to you, and dead load, there is an additional dead load because slab generally have tiles or carpet or something, so there is an additional dead load. Superimposed permanent dead load is 1 kilopascal, so we need to add on that one because this is the weight of the slab, but additional you might have some kind of a carpet or tiles or anything that will add 1 kilopascal extra. So total dead load is equal to weight of the slab 5.75 kilopascals plus 1 kilopascals, we get 6.75 kilopascals. So that is your G. Short-term factors given to us is 0.7. Basically, when your load when the slab goes on the service, you not immediately get these dead loads because it takes time. So you have 0.7 given to you in the examples. Long-term factors is given to you 0.4 in the examples, and you wondering where those coming from. I think if you remember that one from our previous years, from our SD2 examples, table 4.1 in the AS 1170.0, you have a residential building and domestic, you have short-term factor 0.7, long-term factor 0.4. That's what is taken from, if you remember from our SD2 class. But it's given here, but I'm just taking the reference where this is coming from. So now you have all the factors to calculate FD effective, which is the effective design shear, effective design shear service load. So KCS to dead load plus short-term factors plus KCS live load factors times the live load. So KCS we calculate 2, G we have 6.75 kilopascals, short-term factor 0.7, KCS2, long-term factor 0.4, and the live load Q is given to us in our examples. Live load is, where is it? Live load 2 kilopascals. So let's put that 2 kilopascals there. 2 kilopascals. So if I just work it out, that 0.7 plus 2 times 0.4 times by 2 plus 2 times 6.75, you get 16.5 kilopascals. And don't play with the units, they have given you that kilopascals. Okay, so the FD effective is a kilopascals. Now we have all the parameters that we can use these equations, so I can write it down again. L0 on D less than or equal to K3 K4 delta on L0. I am not writing L effective, I am writing L0 to just align with our example. FD effective and 1/3. So let's plug the value. L0 we calculated, right? You remember L0 0.7A supports and so on. If you want to use L effective, don't hesitate, 5150. If you want to use L0, 5045. So let's, for our example, let's use 5045 millimeters. This small d we need to know the depth of the slab. K3 we got K3 equal to 1. I think I can show you. K3 equal to 1, K4 1.75. K3 equal to 1.75, delta over L0 1 over 500 given in our example. I can show it to you. Delta over L0, we have let's clean up this one. Delta over L0 1 over 500. So that's I plug, and then you have 1000 as it is. EC we just get it, and EC in megapascals. Don't change any units or anything. I think 26,700 megapascals, and that is also given in the standards, that EC you need to take it into megapascals. That is just written down here. So let's put the 26700 megapascals over FD effective is 16.5 kilopascals and 1/3. So don't forget to multiply this 1/3. So let me find this one. 1 over 500 times by 1000 times by 26700 divided by 16.5 to the power of 1/3 times by 1.75. You have 25.89. So 5045 millimeters less than or equal to 25. Please keep an eye on this one. So look at that L on D ratio. Which one? How much we use? L on D ratio we use about 22, right? So L on D ratio here is 26. So keep an eye on these numbers physically. Don't just get this number 2500 or 10,000. You might screw up something. Keep an eye on this number. It's almost around range 20, 25 or 30 in that range. So if I want to calculate this 25.89, let's put this D minimum. That is, this is the minimum that at least we needed. So 5045 divided by 25.89, you have about 195 minimum of D minimum. Okay, so you need at least 195 millimeters. Now what is 195? What is D, by the way? This D is like if you have this Rio, generally in the slab we use N12 bars, like a 12 millimeter diameters. So this is your D. Basically you have DS and your cover is 25. We don't use fitments here, so don't worry about fitment, and cover 25 millimeters given in our examples. They told you to use 25 millimeter cover here, so that's cover is given to us. Now so if you want to calculate this, if you want to calculate DS, then you just need to add some more values there. So I'm basically interested in the D, right? If I want to know DS, then you have this D, which is 195 millimeters plus these 6 millimeters, because I am using this, and then 25 millimeters. So basically my DS minimum, so basically you have 195 plus 6 plus 25, then it's just DS minimum. So 195 plus 6 plus 25, you get 226 DS minimum, right? So look at that number, 226. How much we assume? How much we assume trial depth? We assume trial depth 230 millimeters, and we got 226. Well, spot on, right? We need at least 226, and we have used 230. So our trial depth is 230 millimeter, which is greater than your required DS minimum, which is 226. So it is okay. It is good, right? This satisfies these conditions, 233 millimeters. So we can continue use DS equal to 230 millimeters. There is no any issue for us to use 230 millimeters. Now, this 230 millimeters looks thick, meaning that, look, you can keep trying and keep trying, and you can optimize the slab design. Optimize the slab design, meaning that you might end up using DS equal to 190 millimeters, because optimization, because you don't want to, your client need to be, no need to spend money on what you not needed. So let's optimization. We do several trial, and from this several trial, let's try DS 90 equal to 190 millimeter instead of 230 millimeter. Now the immediate questions come from my students saying, "Ooh, that is tricky, because how comes you reduce 40 millimeters with optimizations? How am I going to know in my test or in that one optimizations in our in our exam or test. No, you don't need to do the optimization. You continue working on 230 millimeters as your starting point, and you continue the design. That is no any issue. You don't need to do the optimization 190 millimeters. This optimization I'm just following from the book, and we have a solution. So I just want to show you that 190 millimeters. But if you follow with 230 millimeters, you no need to worry about it. Just for your informations, that once you've done the 230 millimeter, you need to repeat the whole procedure until you get the smallest depth that will satisfy everything. So that's what the optimizations come from. Okay, generally the engineers use the Excel sheet to repeat that procedure. So let's try now, instead of ds equal to 190 millimeters, right? So that is the starting point. Now look, forget about everything that we started. We have not started our example yet. This is the starting point. This is the now we started. All these things that we done is the rough work. Rough work meaning is just let us to start point. This is the start now. This is the 190 millimeter is the starting point now. Starting point. Right? Starting point, right? You understand that what I'm meaning by starting point, because our example is start now. What then you might say, what have you done so far? Now so far what I done, I just done the deflection check, meaning that my 190 millimeter 230 millimeters is enough to start with, and they will not deflect. So that is the starting point. So therefore this now example has started. Now as you remember, we need to satisfy this ds, that it will not crack, it will not deflect, it will have a, and then we need to provide enough reinforcement. Those things we need to check. Now to do this one, we always need to work out the moments, design moments, how much slab will have a design moment. Then from that we will provide the reinforcement, right? So design moments come from bending moment diagram. So let's calculate the small d first. If you remember the small d concept, let's say you have this Rio, and this is your small d, and this is your ds. So if I want to calculate small d, ds minus cover minus Rio divided by 2. We don't have fitments here, so 190 millimeter ds, cover 25 millimeters given in our examples. 25 millimeters cover in our, we are using 12 millimeter Rio. Okay, generally in the slab we use N12. Okay, we don't use this N16 and so on. We want to provide, why someone might say, why you use N12, why not N16? Look, we want in the slab, we want to provide more Rio with the closely spaced Rio to avoid the cracking due to the shrinkage, and because you can see the slabs are wide and narrow. Sorry, they are thin and wide. So we want to provide the, okay, so N12. So you can see that N12 as you can see the N12. Why we provide N12? Because you can see these are the Rio that we want to provide the, because you might put these N16 or N20, then you need to provide less Rio, but the spacing would be large, and then you will have a crack. That is not good. So in the slab we generally use N12. Okay, that's what so N12 159. So everyone agrees so far, 159 millimeters is the depth. Now we need to look, I have to give you this one, like in the, so far I have not shown this one. If someone say that, okay, we pull, you have this simply supported beam, and you have W and you have L, what would be my design moment? You said, oh, I draw bending moment diagram, and this WL square over 8, this is my M star, positive M star. That sounds good. We teach you in the mechanics of solid, we teach you in the structure analysis. That's how we do the bending moment diagrams. That's how we calculate the design bending moment, right? Design bending moment. And in the, even in the beam as well, you done these ones, and we give you this. You remember in the test we generally give you this. Now in the slab, generally we have a structure analysis given to us. Now please note, this is kind of information that you might need to keep it, because it's very useful. I have only few minutes, 5 minutes, but let me try to help you out. So we have this close to calculate the design simplify method for structure analysis. So we have this, you can see this negative design moment, positive design moment, and shear as well. By the way, clause 6.10.2.2. So this is the bending moment diagram. Why? Because you have a continuous beam and the moment distributions and so on occur. So let me explain you how you read those clause. Right? So let's say you have a any typical sections. Let's say you have a any typical cross sections that you have. Let's start with let's say you have slab or beam and it has just a two span. You have this two span beam. So let's say this is two span slab or beam. So this is, let's say this is slab or beam. All right, and these are the supports. Now, or you might come across with continuous. Let's say this is keep going here, and then you have these continuous supports, keep going, and it is continuous, right? Now this is again continuous. Let me write continuous slab or beam. Now in that case you need to find the moments, right? Because if I draw this one typically in this fashions, let's say two span, this is your beam or slab, you might have this bending moment diagram, right? This is typical bending moment diagram. If you have continuous, then you have this, and then you have this bending moment diagram, something like support negative. In between the supports you have this positive, so you have this negative, this is negative, and this is positive moments above the lines. So now my question is, what is the moment here? 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 Let's say you have this loading given to you, right? So that is the questions that I want to answer it in this clause. Now let me help you out, meaning that, okay, let's say let's start with positive. Let's start with easy one, positive. Let's start with here and here, positive bending moment. How are we going to do it? So if you come back to the clause 6.10.2.3, you have positive design moment. In the end span you have 1/11, and for interior span class and ductility. So that's easy, FD ln over 11. So for end span, so this is end span, so this is your end span. So in here you have plus 1/11, that factor is coming from here. Why are you writing 1/11? Because they are common, FD ln square. So 1/11 you have positive design moment. So what that is 1/11, and FD is this FD. What is ln? Ln is the clear span, right? So I hope you understand that. So if someone asks you to find the design moment here, then you have FD ln square over 11. So that is here FD ln square over 11, or you have FD ln square over 11. So that's what you need to that's what you can just think of that way. In here as well, because this is again end span, so you have FD ln square over 11 positive design moments. So I hope you understand FD ln square over 11. Now the next one that I'm just going to explain you, and then we finish our one. So let's say you want to calculate a negative design moment. So you want to have a negative design moment, clause 6.10.2, and there are various, how many options? 1, 2, 3, 4, 5, 6. There are 6 options. 6 of them I will explain you this one. So let's talk about this first one, that is continuous one. That you have continuous one is here. For interior face of exterior support that will have their supports, you have these 24, or when you supported by column you have 16. So over here our slab and beam are supported with the wall or beams, and we have a slab here, so 1/24, that is the negative. So that's, you can put it here, 1/24. So where is it? Here you go, minus 1/24. So if you want to calculate here, minus 1/24, and if you want to calculate here, minus 1 over minus 1 over 24, meaning minus FD ln square over 24. So that is the moments. I explain you these two things. You have this moment here. If you want to calculate moment here, this is the equation. If you want to calculate the moment here, this is the equation, and that is coming from the close, and this one here, and so on. So I stop here, but I will continue this one tomorrow, this structure analysis, and then we will. I think this example is quite long. Is just adding more details there. That